Is that those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies that can substantially increase one's chances of making such a discovery? Now, I must think the answer is yes, or of course I wouldn't have posed the question. So let me illustrate this with a linked chain of discoveries and inventions, starting with one of my great heroes, and I hope one of yours as well. Who knows who this is? Okay, no, that's not fair. Okay, you know. This is Hickey Camerlionis, who, of course, was the person that first liquefied helium, and without his contribution, I can assure you I wouldn't be here today. Camerlionis was at the turn of the 20th century, that is the late 1900s, in a competition with Dewar to see who could first liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won when he succeeded in liquefying hydrogen, which exists at atmospheric pressure, I think at about 20 Kelvin. But then eventually, certainly hydrogen is the lightest of the gases, but it's far from being inert. And so eventually, Camerlionis was able to get enough helium. I think it was really about the amount of helium that would fill a party balloon today. It wasn't a lot of helium because it was very rare back in those days. And so he tried to liquefy it, and he succeeded in doing that. And then he did with his helium exactly what Dewar had done with the hydrogen. Dewar had pumped on the vapor above the liquid hydrogen, causing hydrogen to evaporate from the liquid, causing it to cool in order to find out where it was that hydrogen solidified. So Dewar tried the same thing with liquid helium, and he pumped on the vapor above the liquid helium, and it cooled, and ultimately I think he reached a temperature of about 1 Kelvin, 1 Celsius degree above absolute zero, but the darn helium never solidified. Now, of course, this was just at the dawning of quantum mechanics, and so people really probably could not have understood why helium won't solidify under its own vapor pressure at any temperature. I personally have cooled liquid helium down to 1/10,000th of a Kelvin. It's helium-3 actually, and it stays very happily in its fluid state. But eventually, Camerlionis sort of gave up on this experiment, but in fact looked around for some other interesting question of the day that he could answer with this remarkable set of refrigeration processes that he developed. And so there was an argument as to what happened, I shouldn't say that yet, what would happen to the electrical conductivity of very pure metal as you cooled it to absolute zero. So one school of thought was that if it was a very pure metal, as you cooled it, you eliminated the lattice vibrations that scattered the conduction electrons, and slowly the electrical resistance would drop to zero. The other school of thought, however, was that at some temperature, the conduction electrons, which were free to roam around the interior of the metal, would recondense on the ions from which they had come, and all electrical conductivity would cease. So Camerlionis obtained a very pure sample of mercury, which is a liquid metal, but very easy to purify. And he gave it to his associate, Gilles Holz. Now, I put Gilles Holz's name up here because Camerlionis was not of the habit of putting his students' names on his research papers. Thank God that wasn't true for my thesis. So Gilles Holz was cooling the liquid helium. So this is the resistance from 0 to 2,000ths of an ohm. Temperature goes from 4 Kelvin to 4.5 Kelvin, and these are his data points in green. And then all of a sudden, at about 4.2 Kelvin, there was essentially a discontinuous drop in the electrical resistance to a value of less than 10 to the minus 5 ohms, which was really the resolution of their equipment. This, of course, we look at this today and we realize right away that this was the onset of superconductivity in mercury. Mercury is a very good superconductor, but in fact it was very exciting at that time. except that I think Camerleonis suspected that one of the weeds had fallen off the sample initially, and it took Jim some time to convince his mentor that this was the actual, what was actually happening to the resistance. So let's look at those research strategies that allowed Camerleonis and Jim to discover superconductivity. First, use the best instrumentation available, and here I'm really referring to the set of refrigeration processes that quite literally allow Camerleonis to look at nature in a new and different realm. Don't invent, reinvent, borrow technologies if you can. Now, these guys were bitter enemies, but Dewar had invented the Dewar flask in order to liquefy hydrogen, and Camerleonis was quite happy to borrow that technology in order to liquefy helium. Look into an unexplored region of the physical landscape, and up to this point, people had only been looking at the vapor pressure of various materials as they cooled them, and looking to see where they solidify. This was the first case where people looked at real physical properties of these materials. And then, so after Camerleonis had liquefied helium, he plumped on the vapor above the liquid helium, exactly what Dewar had done with hydrogen in order to find out where helium solidified. And he spent 2 solid years doing this experiment, and he never was able to get the helium to solidify. Now, we understand today that liquid helium, in fact, remains in a fluid state all the way to absolute zero. And the reasons have to do with quantum mechanics and the very weak attractive interaction between helium through nuclei. But eventually, after 2 years, Camerleonis gave up on this experiment. But in fact, he then looked around for some interesting question of the day that he could answer with this wonderful device. And what he did, of course, was, I think the light screwed up. This should have been, these two got confused somehow. So he asked Jill Holtz to look at the electrical conductivity of the metal to answer this question, which we've already answered, and we, of course, discovered the superconductivity. So, and then after liquefying helium, he tried to solidify it, which he, of course, couldn't do. But eventually what he found was that as he pumped on the liquid helium, at a temperature of about 2 Kelvin, actually 2.17 Kelvin, he found that the liquid helium stopped boiling. And I think we all understand what that's due to. That's due to the onset of superfluidity in helium-4, which occurs at 2.17 Kelvin. And at that temperature, the helium becomes almost a perfect thermal conductor. And so all of the evaporation occurs at the surface. So no one really got a Nobel Prize specifically for discovering superfluidity of helium-4. I got one for discovering superfluidity of helium-3. I'm no one. But in fact, this person came closest, and this is actually someone that I knew. This is Peter Kapitsa, a Russian physicist, who in the bleak winter of 1943 measured the viscosity of liquid helium as a function of temperature, and found that below 2.17 Kelvin, it was vanishingly gone. And for this work, he shared the Nobel Prize in 1978 with 2 very unlikely colleagues whose work had absolutely nothing to do with liquid helium, but that did have something to do with temperatures. And these were, in fact, 2 good friends of mine, Arno Penzias. Well, actually, I knew Arno well. He was, when I was a department head at Bell Laboratories, Penzias was my boss's boss's boss. So that's how far down I was in the chain of command at Bell Laboratories. And this is Robert Wilson. And of course, I think we all know that it was these 2 gentlemen that discovered cosmic microwave background radiation. So, using this device, AT&T had completed some early experiments on satellite telecommunications. The idea was to beam the telephone conversation up to a satellite Telstar. Some of you may remember that actually before that there was the Echo satellite, which was less successful. And then the satellite would beam it back to a ground station. I don't know if any of you guys, most of you were too young, I think. But there was a while where if you made a long distance telephone conversation, particularly Europe or something like that, there were these long delays, and that's because it took time. These things were in geosynchronous orbit, so the signals had to go a long ways up and a long ways back. But anyway, after those experiments were done, this was in fact the most sensitive microwave receiver of its day. This is a horn antenna, which has the advantage that it's not sensitive to signals originating terrestrially on the surface of the Earth. But the key to this thing is actually inside this rather elegant shed here, an inelegant shed, and that was where there was the highest quality microwave amplifier that had ever been made. And we'll talk about that in a minute, I think. But I would like to go back for a minute and talk about what happened before, because in fact, it wasn't always that AT&T was interested in communicating through satellites. This is Karl Jansky, who barely made him out here. And in 1933, AT&T that was the first time they were actually interested in transmitting telephone conversations using radio waves. And so, but they found that there was excess noise that they didn't understand, so they asked Karl Jansky, an engineer, to find out where this noise came from. And so this is, Jansky built a directional antenna and looked at this radio noise as a function of time during the day. And what he found was, in fact, that there was a periodicity to this noise, but it wasn't exactly 24 hours. It was 24 hours minus 4 minutes or plus 4 minutes. Anyway, it was sidereal time, not local time. And as soon as people heard about that, they recognized right away that said that these signals, these radio signals, had to be coming from outside the Earth's atmosphere. They were not terrestrial signals. And so Karl Jansky then wanted to find out where these signals were coming from. But at that point, AT&T management was very practical, and they said, if these signals are coming from outside, from off the surface of the Earth, there's nothing we can do about it, which is certainly true. So they reassigned Jansky to a different project, sadly. And it was actually, I don't know if I have the name up here, Rode Reber, who was a ham radio operator that discovered that these radio signals were coming from gas clouds in the Milky Way galaxy. So that's part of the answer there. Now getting back to Penzias and Wilson, they needed to have a very, very good microwave amplifier, and it was really based on technology that Charles Towns had developed. Now I must say, this was back in 1950 something. Charles Towns is still alive and actually active. He's kind of a remarkable person. Anyway, Charles Towns, and this is Jim Gordon, who had quite a successful career in his own right. Anyway, this is the ammonia maser tube. This is the second ammonia maser that Charles Towns built. And this was not a technology which was terribly useful for amplifying microwave signals. But it was, in fact, another person, Nicholas Bloomberg at Harvard University, who realized that you could take this technology, which had a beam of ammonia atoms, and replace it with a doped ruby rod, and then you cool this ruby rod to a temperature of 4.2 Kelvin, liquid helium temperature. And in fact, that is the technology that was used by Penzias and Wilson. So here's Penzias and Wilson. Back in those days, and I dare say this is 1964, so I became a graduate student in the fall of 1963. No, yes, that's right. I graduated. I swear. Anyway, so back in those days, the data would be stripped out on what we call a strip chart recorder. So here, what happens is the paper is moving underneath the pen, which is plotting the voltage in the horizontal axis. So here they're looking at the noise coming from the antenna, and these are where it's pointed. And then they had a microwave switch that could compare that noise to the noise, microwave noise being generated by a black body at a temperature of 4.2 Kelvin. So that's a very small signal, and that's why they need really good technology. And so here they do a bunch of calibrations, but I'm not going to read this whole thing. In the end, they found that there was excess noise, even though they pointed their microwave antenna to a place in the sky that was known to contain no radio sources. They found that there was this very small amount of noise, and it turned out that if they pointed the antenna in other places, they also found it was 3.3 roughly counting. We now, of course, realize that this is fossil radiation left over from the Big Bang, quite literally. But that didn't occur to Penzias and Wilson, of course, to begin with. They assumed that something was wrong with their apparatus. So I guess they got a big ladder and climbed up inside this horn antenna. And what they found was that the pigeons had been roosting inside the antenna. So they knocked down the pigeon nests and mopped up the pigeon droppings, and I think there were a few badly corroded copper plates that they had to replace. But nothing that they could do would make this excess noise go away. Now, it's kind of interesting. At the same time they were doing these experiments and they had discovered essentially cosmic microwave background radiation, Robert Dickey at Princeton University was, in fact, researching for this radiation, which had actually been predicted before this time. But Dickey was using a conventional tube amplifier rather than a traveling wave tube maser amplifier. And while the noise temperature of Penzias and Wilson's device was something on the order of 1 Kelvin, the noise temperature of Dickey's tube amplifier was something like 2,000 Kelvin. So it would have been virtually impossible for Dickey to see that. But of course, once the signals were seen, I think you can imagine, they imagined what they saw in the signal. Anyway, the bottom line is, in fact, that Penzias and Wilson were given the Nobel Prize for this discovery. So let's look at the research strategies that allowed this discovery to occur. First of all, use the best technology available. And now we're really talking about the traveling wave tube maser amplifier at very low noise. Don't reinvent the wheel, borrow if possible. We heard how so don't borrow possible. And in this case, they borrowed the technology. First of all, they borrowed the horn antenna, and they borrowed the technology that had really been developed by other people. And that's what we all do in research. And I think that if you're a good research scientist, you know what technologies are being developed. And that's a very important thing. So go to meetings. Look into a region of parameter space that is unexplored. Penzias and Wilson's original idea was to make the first absolute radio noise measurements. It was the first time this had ever been done. And so I think quite by accident they discovered something that they had not anticipated. But in fact, this idea of looking at nature in a new and different realm is a good way to make discovery. And this is the last one of these. I say that the most important for last. Understand what your instrumentation is measuring. I mean, it would have been so easy for Penzias and Wilson to say, well, we've got this little tiny bit of excess noise, but we can subtract that from all of our other readings. And they didn't do that. They actually understood what where it was coming from. So now, of course, we know a lot about CMBR, cosmic microwave background radiation. This is thanks to the Kobe satellite, which shows the intensity of that radiation as a function of wavelength. And this is essentially a perfect black body curve The temperature that characterizes it is 2.725 Kelvin. So this, in fact, is the 3-degree background radiation. And my voice is going to go. I always like to do that. Okay. So, but it turns out that radiation, this data was actually taken with Kobe satellite. Kobe satellite actually looked as well over the whole sky, and they found that if they looked very candidly, I mean, not very carefully, they would see that the sky was higher temperature in the direction that the Earth was moving, and lower temperature the other. And this is just basically a Doppler shift. But then they started, they were able to subtract this off, and then what they're left with is, well, a very bright band, which is in the plane as we go through a galaxy. So that was pretty obvious where that was coming from. But then, in fact, they got rid of that, and then what they found was, in fact, the sky was filled with uniform, these are spatial fluctuations, not temporal fluctuations, in this cosmic microwave background radiation. Very small fluctuations in the temperature of that radiation. But in fact, they found that these fluctuations were reproducible, which meant it wasn't due to some fluctuation in their equipment. And for their work on the Kobe satellite, John Mather and George Smoot were awarded the 2006 Nobel Prize for Physics for their discovery of the black body formula and anisotropy of the cosmic microwave background radiation. So since then, we've had even better satellites. Well, this is something called the microwave anisotropy probe, and it shows these fluctuations in the temperature of that radiation with much higher resolution. The W is for David Wilkinson. Now, David Wilkinson had actually been a member of Robert Hickey's team at Princeton. They were actually searching for this cosmic microwave radiation at the time that Penzias and Wilson actually discovered it. So David Wilkinson was actually on this project. The problem with these satellite-based projects is you never know when the satellite is going to go up. And so sadly, David Wilkinson died before the satellite went up. So that's they essentially named this satellite thing in honor of David Wilkinson. So now I'm shifting gears. This is another one of my images. This is a very small piece of the Iguazu Falls, which is the border between Brazil and Paraguay. And this was at a time when there was probably, I would say, 4 times normal water going over the falls through a series of nightly thunderstorms. Anyway, this is kind of a remarkable picture. There were 2 women who were taking care of me and my wife, and one of them says, "Oh, get a picture of the bird." This is a black vulture, so I got a picture of it. Now, actually, the black vulture was over here, but Photoshop is kind of I try to be honest in my photography, but sometimes it was. Okay, so let me get back to the text. The process of advancing science often leads to inventions and technologies that directly benefit mankind. I don't know if photography is actually one of them or not. However, it is impossible to know from where the advance will come that might solve a particular problem facing mankind. Consider, for instance, nuclear magnetic resonance. Now, I use nuclear magnetic resonance in my research all the time, but it was actually developed in 1946, 1 year after the end of World War II. It's kind of remarkable they were suddenly doing this, but it's probably because of the fact that a lot of advances in electronics were made because of and during World War II. So this is Felix Bloch, who was a professor at Stanford University, and Purcell, who was at Harvard University. And these 2 people invented NMR in 1946, and just 6 years later, in 1952, they shared the Nobel Prize for Physics. And I think, wow, 6 years, that's very fast. But normally, Nobel Prizes for Physics take a little bit longer than that. NMR is quite a remarkable technology. I'll show you why. But I should tell you that before I do that, these were very different personalities. So Felix Bloch was, I think of him as being a bit of a curmudgeon. He was not a warm, effervescent person. And so, you know, these guys went, I know exactly how this works. You go to Stockholm and they give you this nice prize and this diploma. The diploma, by the way, actually cost more than the gold medal. That's interesting. And then, of course, you meet with the press, and the press start asking you questions like, and when they explain how nuclear magnetic resonance works, and so you're talking about processing angular meta and stuff like that, these press had no clue what that's about. So then they pull their ace in the hole out. And that is, well, what do you think NMR might be good for? And I don't have this written down anywhere, but I talked to many people at Stanford University and Harvard University, and the people at Stanford said that Felix Bloch's response was damn little. The idea was that he'd invented NMR in order to probe the distribution of charge in atomic nuclei, and this didn't have any likelihood of having real applications. And Purcell was somewhat of a kinder, gentler, and more thoughtful person. So when asked the same question, people at Harvard claimed that Ed Purcell's answer was, well, perhaps one can use nuclear magnetic resonance to calibrate magnetic fields. And of course you can do that, but that's the least of the value that is represented by NMR. So eventually people were able to create very homogeneous magnetic fields, and then when they did NMR, they found that organic molecules, actually the protons, hydrogen nuclei, didn't all resonate at the same frequencies. There were, first of all, splittings of triplets and quadruplets, and there were shifts of a few parts per million. And it pretty quickly became clear that this had something to do with the bonding of these materials. And so almost immediately, NMR became an essential tool in virtually every organic chemistry laboratory. And I dare you to go into an organic chemistry laboratory today, I should add, well equipped, and not find an NMR spectrometer, because it really is something that's been taken over by the chemists. So, but we're not done. You barely see this. There was a Swiss physicist, I suppose, named Richard Ernst, who was actually working in Palo Alto, but had nothing to do with Stanford University. And he realized that if, at that point, the way you do NMR, you'd apply a very weak magnetic field, oscillating magnetic field perpendicular to the static field, and then that weak field could be thought of as two counter-rotating fields, and so that basically would cause, if they're rotating at the same frequency as the spins precess in the magnetic field, that would then allow you to tip the magnetization. But it was a slow process, and what Richard Ernst decided was that if you applied a very powerful rotating oscillating magnetic field, you can think of that as rotating, that is, break it up into two counter-rotating things. The only one that spins would see are the ones that are rotating in the direction that those spins are precessing in the magnetic field. And so this was basically led to the invention of pulsed NMR. And so this, in fact, very quickly won the Nobel Prize, but people suddenly could easily measure molecular bond lengths, and that's really what was good for. So Richard Ernst received the Nobel Prize in 1991 for his contribution to NMR. I should point out that Richard Ernst, well, first of all, notice it's in chemistry, because that's actually where the value of this is. So I would guess it's chemists that had nominated Richard Ernst for the Nobel Prize, not physicists. I don't know. Probably the case. Richard Ernst actually, at this time, had been working with another Swiss physicist named Kurt Buttrecht. And Kurt did not share the Nobel Prize with Richard Ernst. And so, there are these meetings and you meet all of these guys. And so I was talking with Fred and I said, gee, when Richard Ernst got the Nobel Prize all by himself, he must have been disappointed. He said, no, I wasn't disappointed. I was mad. and so, actually, it's amazing. I think anger or irritation can lead you to do things that you wouldn't normally do. And so what Kurt Woodrick proceeded to do in the next several years was develop pulse NMR sequences which allowed him to determine the three-dimensional conformation of complicated organic molecules. This is a simple protein. A bovine pancreatic trypsin inhibitor, whatever that is. I am not a biochemist. So for his contributions to NMR, which was developing all these complicated pulse sequences, Kurt Woodrick, this is 2002, and Richard Ernst was 19, oh, I'm going the wrong direction. 1991, so it's 11 years later that Kurt Woodrick won the Nobel Prize. Now, there's another Nobel Prize actually from NMR, and this is actually my cell, but this was back in 1971, I suspect. I had a mixture of liquid and solid doing 3 inside the cell. And I'd seen a phase transition, I'll talk about that in a bit, but I didn't know if the transition was in the liquid or the solid. So all helium-3 nuclei had the same spin, and so I did an NMR experiment. How do you differentiate? Well, I actually went to Michael Fisher, who's a theoretical chemist, and I asked Michael to explain to me how he thought solid helium-3 would grow inside this mixture of liquid and solid helium-3 at a temperature of over 2,000 degrees, absolute zero. And he said, you physicists never worry about surface tensions. So surface tension will prevent the formation of little droplets of solid. I mean, it's not going to, I suggested maybe it would be like snowfall. And he said probably it'll nucleate somewhere on surfaces inside your cell, and then probably all subsequent solid will grow on the surfaces. And so I thought about it, and I said, well, if that's the case, then if I apply this is the static magnetic field from an NMR experiment, and I arrange something larger at the bottom of my cell than the top of my cell. And then if I scan the frequency, this is the RF coil that produces this tickling field that can be broken up into 2 components, one processing with the spins and the other counter processing. Then if I sweep that frequency upward, in fact, this resonant layer will move downward, and I can plot out the NMR signal as a function of position inside my cell. And I claim this, in fact, was published in 1971, and actually the inventors of MRI, at least one of them, read my paper, Paul Lauter, who, so these guys, in fact, invented much more sophisticated technology, but based on the same idea, the idea of applying successive the 3 field gradients in 3 separate dimensions. Then, in fact, you can actually get very detailed 3-dimensional images of things like human knee. Now, I happen to know that this is a very healthy human knee, but in fact, my knee now is made of titanium. One of them, the bad knee is made out of titanium, so you can't do this. But in fact, you can see that the meniscus, which I didn't have in the titanium before. Now, I don't know, it's all made out of titanium. But this is a remarkable technology, and I think it's been vastly important in medicine. And so, for their development of MRI, Paul Lauter and Peter Mansfield won the 2003 Nobel Prize, not in physics, not in chemistry, but in physiology or medicine. So it's kind of remarkable that one technology, in fact, can lead to Nobel Prizes in 3 different categories of Nobel Prizes: physics, chemistry, and physiology. So I don't know, this possibility that there might be a fifth Nobel Prize for NMR, but I'm beginning to think I shouldn't pull like that. Just a minute. Okay, so this is functional MRI, and basically what you're doing is looking at NMR signals. You're looking at the rate the spins recover along the magnetic field, and it turns out that depends upon the oxygenation state of hemoglobin. And so what you're looking at here are, in fact, those places in the brain that are actually working, that are processing information. And so, you know, I think this is kind of really neat stuff, but it has to be used to do something you can't do with other techniques, and I'm not sure that's been done yet. This was actually invented by a research physicist from Japan that was working at laboratories with a guy named David Tang at Bell Laboratories, and they invented the safety Ogawa is the person that gets credit for it. So now I'm going to talk about my discovery, the story of my discovery. And I talked about these things rather superficially, but I obviously know more about my discovery perhaps than anyone else. I would hope so anyway. So to begin my life with the beginning of my life, I should report that I was born. This is for David Copperfield. This is my father, who was a medical doctor. My mother had been a nurse but gave up nursing to raise 5 unruly children. I dare say the most unruly was this one here. That's me. My older brother went into medicine. Anyway, my father actually seemed to. So this all started out, I guess, one Christmas day when I got an electric train for Christmas. And by the time Christmas dinner came around, I'd taken apart the locomotive with the electric motor out. And you know, I'm sure there are families where if the child did that, they would get a spanking and go to bed without their dinner. But my father was fascinated with my fascination, and he started bringing things home. He was a medical doctor, and he would talk to his patients. And he had one patient that worked for the telephone company. So one day he came home with a box full of relays and batteries and things like that. And I took a solenoid actuated relay and connected the solenoid to a 22.5-volt battery. And when I removed the leads, I got shocked. And you know, and my father actually understood what this was all about. He said, well, okay, what's happening is when you're interrupting the current, the magnetic field will very quickly go to zero. The changing magnetic field generates an electric field. Anyway, so he was actually pretty good. But I put this thing, packaged this thing in a duffel bag and took it to school, 4th grade. and so there was only a lamp cord sticking out, and if you squeeze the 2 prongs that normally go into the wall together, when you remove, when you let them go apart, you get shocked. And the kids were lined up 20 deep in the play yard. Now, I think under other circumstances, I might have gotten kicked out of school for that, but luckily that didn't happen. This was the start of my career. I dare say I'm one of these people. I think it's true for a lot of young people that they're lucky to survive their childhood. Surely I'm one of those people. So I would say in school, in public school, it was not my physics teacher that inspired me. In fact, it was quite the opposite. This was just after Sputnik. And so there was a new physical sciences study committee physics text. The first half was all Newton's laws, and the second half was all electricity and magnetism. I couldn't wait to get there, but it turned out I think the teacher actually didn't maybe understand that material, or at least didn't know how to teach it. And so he went so slow as to be sure that we would never get beyond the first half of that. I was very disappointed. But in fact, the person that really inspired me was this person here. This is William Hawk. And unfortunately he died, but he was my chemistry teacher. And a lot of these kids, so here I am, by the way. And then these three guys, subsequent guys, they were my partners in crime when we were making bombs, things like that. I grew up in a logging town, Aberdeen, Washington. How many of you guys have heard of Kurt Cobain? Okay, most of you, yeah. So his father and I were high school classmates. That's my main claim to fame amongst the younger generation. Anyway, so actually this is how close he was my debate partner. But what really popped, I mean, it was a standard chemistry course that he offered, but I think there were two occasions where he came in, and rather than talking about what was in the book, he talked about what research was all about. And so one day he came in with a milk carton, and there was something inside the milk carton, and he showed it here. He said, research is like trying to find out what's inside the milk carton. Now, you can do an experiment, and every time you do an experiment, you're asking a question of nature. But nature's answers aren't what's inside the milk carton, something about what's inside the milk carton. So then you have to do more experiments, asking more questions in order to constrain nature's answers to the previous questions. And to this day, that is the way I think about research. It's you against nature. You're trying to cheat nature into giving up one of her secrets. And that's really what's, to me, always been the most exciting and fascinating thing about research is to make a discovery in science is really learning something about nature. And of course, we all think about nature as being a woman. And of course, if you ask a woman questions, the answers are very, very complicated. Depending on the question you ask, of course. Anyway, so to this day, I guess it was when I got the MacArthur Prize. I was one of the first 21 MacArthur Prize fellows. And so I thought about who had influenced my career, and I immediately realized that the most important person was William Hawkins. So I called him up. He was teaching in Los Angeles. So he had gone to Los Angeles and been teaching from Aberdeen, Washington. But in fact, he found that the students wouldn't give him the respect he felt that he deserved. And so he actually stopped teaching. He was really ashamed. And went to work for the Food and Drug, FDA, Food and Drug Administration. But anyway, I called him up, and we talked for a long time. And then periodically I would call him up, tell him how things were almost up to the time that he died. I can't remember when he died. It was sort of sad. But this was, for me, it was a wonderful person. And all I can say is that if any of you have had someone that has inspired you, let that person know. I think it's very important. Well, I suppose Richard Feynman inspired a lot of us, but I then left. I graduated from Weatherwax High School. Weatherwax was, I think, one of the founding fathers of the town or something like that. And I went to Caltech, and this was when Feynman had just stopped teaching his famous 2-year course of Feynman Lectures in Physics. So he was actually giving some of the lectures, but I would say probably less than a third of the lectures were given by Feynman. And the other professors really struggled in order to keep up with the pace that Feynman had set for these things. So I think that it was sort of interesting. My entering class at Caltech was 192, and only 120 returned for their sophomore year. And I think Richard Feynman was largely responsible for the loss. But of the 120 that remained, I think fully 2/3 of us wanted to go into physics. And Feynman is also responsible for that. So he was sort of a responsible. So anyway, I graduated from Caltech, and I really, at this point, I was actually working in an infrared astrophysics group. So I was usually going up to Mount Wilson Observatory and running this survey telescope. One night I was up there, 2 other guys from the infrared group used another telescope to discover the center of the Milky Way galaxy in the infrared. You can't see it in the visible. And so I like to say that mine was the 3rd set of human eyes to see the center of the Milky Way galaxy. Of course, it's in the infrared. So what you see is a bump on a strip chart recorder as the telescope scans across that region. But you cannot imagine how excited I was for that to happen, for me to have actually seen that. And so then I applied to 8 universities for graduate study, and I only schools based on whether they were good in astrophysics or not. So luckily, Cornell University was one of the schools that I applied to. But then, I think, in early March, before one had to make these decisions, I started thinking about what I loved doing. And it wasn't astrophysics, it was really this whole business about asking nature questions. And you can't do experiments in astrophysics. You cannot change the temperature of a star and see what happens. And so I really wanted to do experiments. And then, there was no one at Caltech in condensed matter physics, which is where you can experiments are typically short, maybe anywhere from a week to 3 months or something like that. And so it was in March, who was it? I'm sorry, but when you get old, you forget names really badly, and I'm getting there now. Anyway, I talked to someone who suggested what schools were good. Moscow. This is the way it works, by the way. As soon as you don't try to think of it, you come up with it. So Mossbauer would actually, part of the work that he did that won the Nobel Prize was done at Caltech. So he would, every March, he would come to Caltech. And I asked him where I should go, and he looked at the list, and he said, well, there are only 2 good schools in the United States in condensed matter physics, and you didn't apply to either one. and they were the University of Illinois, which of course produced the BCS theory just a few years before that, and the other was UC Berkeley, which was actually still a very good school in condensed matter. I said, well, but of the schools that I did apply to, he said, well, probably either University of Washington or Cornell University. So I didn't want to go back home. University of Washington I grew up in Washington State, so that's how I ended up at Cornell University. Far above Cayuga's waters, with its waves of blue. Well, anyway, my heart is at Cornell. Anyway, so I went to Cornell, and I didn't know what I was going to go into. I was interested in condensed matter physics. There were 2. There was a physics colloquium and a solid state seminar that first semester, and it really changed my life. So, well, that changed my life too. Well, I guess I'll get to the other in a minute. So when I showed up at Cornell, it was before the fall semester started. You had to find housing. There was essentially very little graduate student housing. So I went into the women's graduate cafeteria. Women's graduate dorm cafeteria. And there was this little Chinese girl sitting all by herself. We were the only 2 there. So I quickly got some food and sat across the table from her. And that was this person here. She's sitting right there. And so we talked for a while, and I invited her out. So I can't remember. Turns out she liked movies. Cheap date. So we did a bunch of movies, and then the fall semester started, and I would call her up and say, how about a movie? And she was not interested at all. I guess she would say, too busy. And I claim that's what happened. She will tell you that she was not quite so rough. But anyway, and so eventually, after we were married, she explained that her parents had sent her to Cornell to get an education, and that didn't include any of the stadium visits. But after our 3rd year of graduate study, she actually got her PhD in 3 years, and it took me 5 to get mine. So she was doing around my life, and that's when I proposed that we get married. We've now been married for 42 years. So getting back to physics, there were these two talks. One described something called the helium-3, helium-4 dilution refrigerator. So you start with, basically there's a still here that has a mixture of liquid helium-3 and helium-4. Helium-3 is lighter, and so in fact, the vapor pressure is mostly due to helium-3. And if you pump on it, you're pumping off helium-3 atoms, and then you basically put them back in the refrigerator. And there's this thing called a mixing chamber, where the top is essentially pure helium-3, and then below this is 6% helium-3, and the rest is superfluid helium-4. And the helium-3 atoms go through the superfluid helium-4 as if it weren't there. And so then these helium-3 atoms come through here. But if you think about what's happening, every time a helium-3 atom goes from this concentrated phase to the dilute phase, the entropy increases. Now, if you do this reversibly, that entropy increase comes from the absorption of heat from the outside. And so the prediction was that you could get down to temperatures somewhere on the order of 10 to 20 thousandths of a degree continuously by using this process. And so actually, as a first-year graduate student, I built a helium-3, helium-4 dilution refrigerator. So this is a mixing chamber where the cooling occurs. The still is out here, you can't see the pumping line. These are heat exchangers which allow you to cool the helium-3 that's returning, so that by the time it reaches the mixing chamber, it essentially doesn't present a heat load, but rather, in fact, it facilitates cooling. So there was another technology, though, that was described in another talk, and that was a result of a conjecture by a Russian theorist named Pomeranchuk. Now, Pomeranchuk was a member of the Landau school. These guys were extremely broad. So Pomeranchuk was mainly interested in high-temperature plasmas. But when he heard about liquid helium-3, and that's actually another story, but probably for another talk. Helium-3 essentially does not exist in nature. It results from the decay of tritium. And so it was in the basically late 40s that people started trying to build hydrogen bombs, and so they were producing tritium. The tritium decays with a half-life of 12.4 years in the helium-3. And that is all the helium-3 that I've ever studied started out with as being part of a nuclear weapon. In fact, you actually built the helium-3 out of hydrogen bombs through a process which I won't explain. So anyway, so Pomeranchuk thought about that helium-3 atoms are Fermi particles like electrons. And so electrons at very low temperatures, the entropy of the electron gas is linear in temperature. And so we assume that would be true for helium-3 atoms as well. In the solid, you have very high positional order, but in fact, each atom on a lattice site in solid helium-3 can either have its nuclear spin pointing up or pointing down. And that gives you an entropy of R log 2. 2 is the number of states available. That's this line here. And then at some very low temperature, nuclear spin ordering is expected to occur in solid helium-3. But you have a very unusual situation below where these two curves cross, that liquid helium-3 is more highly ordered than solid helium-3. It's a very unusual situation. And so then Pomeranchuk realized that if you started with liquid helium-3 and you compressed it, once you reached the melting curve, you started converting liquid to solid. In fact, you go along the melting curve to lower and lower temperatures. And so ultimately, the expectation was you could reach temperatures of order 1,000th of a degree. So I actually built this. Now, this was my third year of graduate study, I think, and I had a horrific skiing accident. That's why I have a titanium knee now. But it was while I was laying in the hospital bed that I actually designed this piece of apparatus, which is my Pomeranchuk cell. The helium-3 is very expensive, so I do it in roll here. This is helium-4, and it's just a hydraulic press, and we're decreasing the volume here. That raises the pressure and causes some of the liquid to be converted to solid. And so then at the end of the third year of graduate study, something else happened to me, and that was that Liu Xijun, this girl from Taiwan that I met the day that I showed up at Cornell University, and I got married, and we've now been married for 42 years. She's a biochemist and I'm a physicist, and we actually do talk occasionally. Anyway, I should tell you there was a very nice little formal garden that was kind of in back of the White Art Museum, which is right next to the physics building. I didn't have to miss any field points. That's a joke. Anyway, so then I still didn't know what to do. So she actually got her PhD in 3 years. And so she was going to go out of my life if I didn't marry her. And so then she got a postdoc, and I asked Dave what I should do, and there had been someone named John Wheatley, a famous temperature physicist, who looked at the shift in melting pressure of helium-3 as a function of temperature and magnetic field. And the theory suggested, in fact, that this is with zero magnetic field, this is set as flat, there's no shift. And then as you apply a magnetic field, as you go to lower temperatures, there's a larger shift depending on what the magnetic field is. And the large magnetic field would exist. But in fact, this field, which is 12.9 kilogauss, should have had the shift should have been, as I showed you. And John Wheatley, this famous physicist, saw a huge effect, which looked very exciting to me. So we said, why don't you go in and try to reproduce those results? And that's always an important thing to do if you're starting off where someone else has left off. So here are my data, and you can see, in fact, they're entirely consistent. It's very simple thermodynamics. So this surely did not look like it was going to be a Nobel Prize winning experiment. In fact, it looked terrible. Then things got worse because in order to do this experiment, I obviously needed a magnetic field. There were 2 other students in the lab that were waiting for this iron core electromagnet. This thing weighed about probably 5 or 6 tons. And so they went to David Lee and Bob Richardson, professors, and argued that I should have to give up this magnet to them. And the professors agreed, and because of that, they shared the Nobel Prize with me. Because there wouldn't have been a Nobel Prize if, in fact, I continued doing that experiment. And so then, I decided, well, my prize tag's full. I might as well see if I can do something without the magnet. So I said, I will compress at a very constant rate and look at how the melting pressure changes as I cool. And so I started at 22 milliliters, and here now time is increasing to the right, pressure is increasing upward. And here I rebalance the rates of measured pressure is continuing to rise, which means it's cooling, which is good. And then all of a sudden, this point that I later labeled as A, there was a very sharp decrease in the rate of cooling, and of course I was very unhappy to see that. So I decided this was actually, that if you go back and look at your calendars, how many people have a 1971 calendar? I assure you this is the day before Thanksgiving, 1971. And so I decided I would use the 4-day holiday to pre-cool the helium-3 in my Rundstedt cell to the lowest temperature I could possibly reach. So I start this again now. This is after that weekend. So this is the Monday after Thanksgiving break, which was basically a 2-day break back in the old days, Thursday and Friday. And so here I'm going fast to the balance of bridge, and then all of a sudden I see this thing, the same thing. And I went back and I found that the pressure where this occurred before, and this time, and hence the temperature, because the pressure and the temperature are related, was the same within something like a part in a million. And it seemed extremely unlikely to me that this could be some chance heating event, given how highly reproducible it was. And so I let this continue to go, and then eventually I saw a little tiny drop, which I later labeled as E, but I had no idea what that was in there. Eventually I found that both of these features, which I called the first one A and the second one B, which is science. first, we actually called this the glitch, and this was the second glitch, but you have to give you some scientific names, A and B. I could see it on cooling and also on warming. And so it had to be real. And so in order to decide whether it was in liquid or solid, I invented this technique which I've already talked about, which allowed me to differentiate the liquid NMR signal from the solid NMR signal. And so here is some practice some data. Now, in fact, time is increasing to the left and pressure is increasing downward. These are NMR lines. What's happening is I'm sweeping the NMR frequency to higher frequencies and down to lower frequencies, back and forth. So all of this stuff is a mirror image of something. This is a little bit colder. And this is the liquid signal, and it should have been flat across this region of these high peaks. But in fact, it seemed rather badly distorted. And so I didn't think much of it. I took this data on April 17th, but then in the evening of April 20th, I was reviewing this data and taking more data. And then I looked at what happened to the liquid signal. And it had essentially coincident with this drop in pressure that we call the V, second transition, the V transition. In fact, the liquid NMR signal dropped by a factor of 2. And I knew right away what this had to be due to. So I wrote in my lab book, so this is April 20th, 1972, 2:40 in the morning. This is a very good time to make discoveries. No one is bothering you at 2:40 in the morning. I have discovered the BCS transition, but we treated it. And then, then I explained why. And then I ran around the basement of Clark Hall, the physics buildings, to share this exciting news with some pictures. It turns out there was no one there. And then, except for me. And then in desperation, I went up to the 6th floor, hoping that the theorist would fall asleep in his desk. But in the end, it turns out I was the only human being in the entire physics building. And so at 4 in the morning, I couldn't stand it. I called up my thesis advisor. And I would say that's maybe not such a smart thing. Make sure that you know that what you discovered is significant. Anyway, so I explained to Dave Lee what I'd seen, and Dave Lee called me back at 6 a.m. He wanted more details. So I got absolutely no sleep that night. And Dave Lee, after 4 a.m., didn't get any sleep. Very exciting. I should tell you, it's been interesting because the time that I received the phone call from Stockholm, unfortunately, that's in my computer somewhere, but I can't find it. It'll take a while. So this was at 2:30 in the morning. So the phone rings, and the phone's on my wife's side of the desk, of the bed, but she never answered. So I run around in the yard to pick up the phone. And this guy says, hello, is this the witness Osheroff? And I said, yes, it's 2:30 in the morning. He said, I know that, but I have a matter of some importance, if you would. I am Carl Jakobsen, Secretary General of the Royal Swedish Academy of Sciences. At that point, my jaw drops down to my navel because I know exactly what this phone call is all about. And so that was how I knew that I was receiving a Nobel Prize. And then he said that I think it was at I think it was 4 a.m. He said they were going to release this over the World Wide Web. And I could expect phone calls. And so, sure enough, this phone started ringing at 4 a.m. and I'll do an interview, hang up, and then phone in instantly. And then I'll do another interview. And eventually, the Stanford News Services got hold of me. And they said, can we be of some help? And I said, what can you have? They said, well, we can manage your phone. I said, oh, come on up. Sorry, I got some of these times a little bit wrong, I think. Anyway, so what happened was the doorbell rang at 4 a.m. And I quickly run up. I assume it's the Stanford News Services. I open the door and run back because I'm doing an interview. These are two photographers who are taking pictures of me in my pajamas. Anyway, they let me put a sweatshirt on, as I recall. So anyway, then getting back to 1972, rather than 1996, when I was in the World Cup. So Dave Lee suggested, well, we have this other transition, And let's see what happens at that transition. So if I collapse the magnetic field gradient, and so this is a huge thing. Most of this is solid. The liquid signal should look like this little red thing underneath. What I found is as I go through the A transition, in fact, the liquid NMR frequency shifts to higher and higher and higher frequencies. And then when in fact that B transition, that little drop in pressure, this guy disappeared as it ran back underneath this. So in fact, I discovered not one, but two phase transitions in this mixture of liquid and solid three. So we basically looked at these frequency shifts as a function of magnetic field and temperature. Here, this is actually melting pressure. And we found that all of the data collapsed on a single curve if we plotted the liquid frequency squared minus the solid frequency squared. So I sent a preprint of this to Tony Leggett in England. Tony Leggett explains this whole thing here rapidly. So we're almost done. Let me just talk about the research strategies, utilize new technologies to view nature from a new perspective or in a different realm. And so, I was literally the first person who was actually looking at things at these thermal temperatures. Don't give up when things are going badly, like when they take the magnet away from you. Failure may be an invitation to try something new. And so it was only after they took the magnet away, which would not have allowed me to complete the experiment that I was supposedly going to do for my PhD thesis, that I made the discovery. And so I say, spend a little bit of your time doing something different. Curiosity-driven research is fun and it can be rewarding. And this is actually, my wife is Chinese, obviously, and so I probably know maybe a dozen phrases in Chinese. So my wife, Fresno was offering at this time a course in conversational Chinese. So you didn't have to learn all these complicated characters, which is and so I thought, wait a minute, this is the last chance for me to actually do anything that will give me a job in physics. And so I don't know much Chinese other than things like Xiao Su Wa La, which means I laughed myself to death. And Ni Zhe Wong, you're dreaming on. But the one I do know and is relevant for today is Jin Tian Tian Xi Hao Ji Le. Does anyone know what that means? No Chinese here? It means today is a beautiful day. Okay, avoid too many commitments. So I didn't learn Chinese, but in fact I discovered 3 superfluid phases. And then I would say, back off from what you're doing occasionally to gain a better perspective on the task area. And this, I think, is absolutely true. We become myopic when we focus too tightly on our work. So here is now a phase diagram, and I just put this up there because it's quite remarkable. This is the melting plane where I did all my experiments, and you can see this is superfluid helium 3A, superfluid helium 3B is everything below this line here in temperature. But I also showed superimposed on here 2 spin-ordered phases of solid helium. One is called the U2 phase. The other is called the CNN, candid normal anti-thermal. So it's quite remarkable that such a simple atom as helium-3 at very low temperature has 5 ordered states. Really quite remarkable ordered states. So here we are. This is David Lee, my thesis advisor, and me and Bob Richardson sharing the Nobel Prize for Physics in 1996. And Tony Leggett, who explained the nature of basically the frequency shifts that I observed. You can only have 3 people on the Nobel Prize, so Tony had to wait until in 2003. He shared the Nobel Prize with Albert Kossoff and Ginsburg. So this is a BCS Nobel Prize. BCS is the theory that explains superconductivity. So Tony applied that theory to helium-3. So finally, I show my cell examples, and now what I've done is put the names of people who contributed ideas or technologies without any one of which I probably would not have made the discovery. So Edwards and Hall invented the helium-3, helium-4 dilution refrigerator not that long before I actually built my first dilution refrigerator. Block Schrieffer, of course, created the theory that explains superconductivity. That was then applied to helium-3 by Phil Anderson, a good friend of mine. Paul Runchuk is a Russian theorist that had predicted that if you compressed and solidified helium-3, the system would cool. That was essential. Ed Hamel was the person, I actually interviewed him for APS. There was I can't remember, an APS meeting. Ed Hamel was the person at Los Alamos in 1948 who was responsible for keeping the nation's tritium supply clean. So what he did is separated out the helium-3 and he saved the helium-3. And then on his own, he decided to liquefy the helium-3 and measure the vapor pressure as a function of temperature. So, and he published those results, and he said how much helium-3 he had. And he admitted to me that, in fact, that told the Russians something about how long the United States had tritium and how much tritium they had. But, in fact, I think he wasn't punished for that. So, and then Straining Adams invented this very elegant pressure transducer, and Lawton Purcell, of course, invented NMR, and without NMR, it would have been very difficult for me to understand what those kind of stuff. So, in the end, I would say that advances in science are seldom made by individuals alone, but result from the progress of the scientific community asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. And this is really for a talk that I gave to the American, to the National Science Foundation, who funded my research. We have rapid progress. I said one must support scientific research broadly and encourage scientists to interact with one another and spend a bit of their time satisfying their own curiosities. And I think it's very important for funding agencies to recognize that. I'm not sure. Anyway, this is how advances in science are made, often made. And so this is, again, one of my pictures. I just saw a couple of waves going through this. Did you other people see that? What was that picture? Well, it's interesting. Anyway, so this is really a bridge. And let me just tell young researchers that to decline a challenge for fear of failure is to fail at the onset. Good scientists learn almost as much from their failures as from their successes. So good luck, and thank you for listening.
Okay, Dr. Osheroff, that was a very inspiring and excellent talk. I know you are on a tight schedule. Do you have time to answer a few questions?
I certainly do. I'm not. It's going to take me 4 hours to get home. If I'm lucky, they won't be working on Saturday on the road.
Let's hope. Wait, I wanted to pick out your question.
Yeah, so does anyone have any questions? Surely so. Did I do that badly? No. Yes.
So after they took your magnets away, right? I mean,
Yeah.
you're probably a little frustrated and everything. When did you say, well, I got to cool down, I'm going to go ahead and try something? You do it right away?
Yeah, pretty much. You know, the thing is, you know, you had to add liquid helium to the dewar every day, and Dave Lee would tell you every day that helium was expensive and that you shouldn't waste it and stuff like that. Yeah. Yes?
I have a question about the helium-3. There's been discoveries that helium-3 has been discovered on the surface of the moon. Is it viable to go there and get that helium-3? Could it be processed as a type of fuel or something?
I don't know. The interesting question is what helium-3 is good for besides the stuff that I do. I don't know the answer to that. I mean, you can do actually very interesting MRI with helium-3. In fact, there are people that have done that. So you basically have a patient breathe in a couple of liters of helium-3 gas, and then you do an MRI on his lungs. And then you're not sensitive to the protons, the tissue that makes up the lungs, but to the helium-3 gas that's inside the lungs. And so, for instance, if you see a blockage or something like that. So that's probably one of the few non-scientific uses for helium-3, I would suggest. But it expensive. I don't know what it is now, but I think it's probably something on the order of $1,000 a liter of gas in STP. When I was doing these experiments, it was, I guess, $300 a liter of gas.
So
Yes.
does all the helium-3 still come from nuclear reactors or nuclear processes?
It comes from the decay of, specifically from the decay of tritium. Tritium doesn't, its half-life is 12.4 years, so you're not going to find tritium in the environment very much. It's made, I think, using Excel. Does anyone understand that process? All they know is you basically, I think you start with deuterium and you want to add an extra proton to it. And that then gives you helium-3. Not tritium, so I don't know how you do that, but people do. And there, of course, the whole technology is driven was in order to create tritium, and tritium for hydrogen bonds. So you can ask me any question you want. How often do you guys have a chance to embarrass a Nobel laureate?
More questions? Yes.
I have a question pretty good unrelated to your speech, but what did it feel like when you got the call that you knew that you were going to get Nobel Prize?
Yeah, okay, that's good. Okay, thanks for that question. That is, yeah, so let me tell you that people had been telling me for years, and typically, so the prizes are given out early November, I think. And so in sort of early October, people would come up and tell me that they nominated me for the Nobel Prize. Of course, that's a very self-serving thing to do. You're not supposed to do that. That is, nominating is fine. Telling the people that you nominated them is not fine. And so what I knew was that if I got a Nobel Prize, it would turn my life upside down. I was actually not looking forward to it at all. And I would get very nervous every late October that, in fact, this year my life would be turned upside down. And it does. It really does change your life a lot. I think it depends on who you are. I'm one of these people that it's very difficult for me to put that behind me, I suppose, and just continue. Ironically, I would say that the Nobel Prize has had a wholly negative impact on my research. Because, I get invited to go all around the world giving talks. So I actually kept track of it. And looking at how much, I would basically do about 30,000 miles of air travel a year as a prior to the Nobel Prize. And that's sort of typical for scientists going to international meetings and things like that. But the year after I got the Nobel Prize, in fact, I flew 120,000 miles. And the year after that, it went up to 150,000 miles a year. And it's been that way ever since then. So I don't know. I mean, I kind of enjoy traveling. I usually bring an expensive camera with me, and so I have lots of interesting photo opportunities. Some of the pictures you've seen here were pictures I took while giving talks in different countries. Yes?
What frequent flyer mile program would you recommend?
I'm not very good at these things. I'm a United flyer. I chose United mainly because they fly to Europe and also to Asia. And so I do both, and I do quite a bit of both of those routes. So, but interesting question. Yes?
So besides the supersolid, is there any some other research, big research on answer question in helium physics?
Yeah, well, supersolid is a very interesting thing. And of course, Moses Chan, who discovered, I think, supersolid helium-4, has been a good friend of mine. He was in the low temperature laboratory when I was in Texas, so I know him well. And I really think we don't understand to this day really what's causing that, but it's fascinating. I would like to hope that I didn't discover everything that there was to discover. in helium-3, but I'm not sure that that's not the case. So that they're, all of these 5 ordered phases of nuclear accelerator helium-3, I was able to identify all of them. With help from theorists, I should say. A lot of help from theorists. Yes?
If you were a grad student today, what topics might excite you to go after?
Yeah, well, I think you sort of have to also look at what area you're likely to be able to get a job in. And so I think a lot of nanophysics is exciting today. It's very current research. I think it really blends in well with developing technologies. And so, you know, certainly as a faculty member, we've had a lot of talks on nanoscience, not all of them are on nanoscience. But those kinds of areas, I think, are very much in vogue. And do I think it's great to go into an area that's in vogue? I would say probably it's a good idea. You probably get funding, and you could go to meetings, and there are a lot of people you can talk to about your research. But at the same time, don't put blinders on. Spend a little bit of your time satisfying your own curiosity, as I say, and see if there is anything in your research that you don't understand, because that can be some of the most exciting research that you can possibly do. Yes?
Did you ever have any serendipitous moments while you were discovering HE3?
Yeah, well, I think there were a lot of them that were serendipitous. The fact that well, first it was a good thing that I dislocated, that I destroyed my right knee. That was a serendipitous moment for sure, because it was really while I was in the hospital bed. And that is kind of interesting, because what I say is that there probably is a silver lining to every dark cloud, but it requires that you seize the opportunity that's been made available. And in this case, that was when I designed the Paul-Renchuk cell that I used to discover specifically. You had a question.
Yeah, it's more photography, but what kind of photography do you like to do? Do you have a favorite kind?
Mostly, my favorite is clearly landscape photography. I think that I study nature all the time, and nature presents me with all these wonderful landscapes. So, yes?
You talked about all the travel and how your life turned upside down by winning the Nobel Prize. But what is the greatest thing at a personal level for you to be the Nobel laureate? What is the most important part, or the memorable moment?
Yeah, well, look, I mean, it was certainly a serendipitous discovery, and I don't know how much credit I give myself for that. I think I was smart. I went into an area because I saw new technologies that would literally allow me to look at nature in a new and different realm. So I think I did the right thing there. But I think I was lucky. There's no question about that. I think a lot of the research strategies I put up on the screen today are relevant to all of you. So, I think, research should be fun, and it's challenging. That's part of the fun. I mean, nature doesn't give up her secrets very easily. But as a scientist, you are a member of an international community. It's really great to go to other countries, foreign countries, and talk to people, and then maybe photograph their scenery. Yes?
Is that something, two-part question?
Two-part, those are complicated questions. Maybe I can do one more. Go ahead.
This helium-3, when it's in its super fluidity state, does it exhibit the same characteristics as helium, as normal helium? And if it does, by the strange characteristics, I mean, like second sound, superfluidity, stuff like that. And if it does, do you see any practical applications for that in the far future?
Well, to answer the last part first, because it's very easy, no. So helium-4, you have to get it down below 2.17 Kelvin in order for it to become superfluid. Helium-3, you have to essentially get a factor of 1,000 lower in temperature. So I don't think it really has any commercial uses, particularly because helium-4. So the bottom line is helium-3, because of the underlying the fact that it's really a BCS condensation. Its properties are really considerably different. The coherence length in helium-4 is very short. Coherence length in helium-3 is roughly a factor of 1,000 longer than that. But in principle, one can create vorticity in rotating helium-3. People in Finland have done that very nicely. There was, I think, yes?
Assuming that you had other areas that had been striking your interest at the time, what specifically made you pursue that venture with helium-3?
Well, as I said, it was helium-3 research was, I came in as a graduate student and there were these new refrigeration technologies. I mean, the idea that if you compress and solidify something, then it would cool almost to absolute zero seemed really bizarre. And so, I found it seemed very counterintuitive, and that's part of the reason that I was attracted to helium-3 physics. But I dare say that almost everyone in the low temperature group was doing helium physics, either helium-4 physics or helium-3 physics. And so it wasn't that I was a renegade doing something very different from what other people were doing. Yes?
Indeed, today we have some engineering students in the audience. So if we want to recruit them to join the physics major, what do you say?
Yeah. Well, first of all, I think that there's nothing wrong with engineering. I think that if engineers do very different sorts of things, though. I mean, they don't trick nature into giving up their secrets. In fact, I think that every experimental physicist at some level is also an engineer. I built the Bush refrigerator, the Pomerantz cell. I had to worry about strain and all of these strength of materials. That's engineering, that's not physics. And so I think, a good experimental physicist is part engineer. Thank you.
I actually can't, is there maybe one more question? Because I just noticed that we're behind schedule as far as getting the, no. So actually that's my sorry. I just looked to watch the schedule. So I just wanted to see, is there maybe one more last question for Dr. Osheroff? Okay.
So, how does the fact that helium-4 is a boson, helium-3 is a fermion, result in different properties for the two materials? And that's kind of heavy.
That's one of these exceedingly deep questions that I don't really understand, but it's exactly, I mean, this business that makes superconductors superconduct. Okay, the conduction electrons have these properties and I must say, that Bardeen Retriever, they explained it, but they didn't anticipate this because superconductors already existed at the time that the BCS theory came out, obviously. It would have been remarkable, I think, for BCS to have predicted superconductivity. And I don't think that